The simplest example of distribution are binomial distributions, and much of the theory of probability starts with binomial distributions, from 19th century on. So in binomial distributions, you do n measurements, and you have R successes and the rest are failures. So the measurements are binary. Either I get something or I don't get something. And you can use frequentist method to compute the probability of a success or a failure. So if you have n trials, what's the probability of R successes? So n trials are successes, repeated success. This is just a binomial, so this is a number of ways in which you can pull out one out of n ones and zeros if you don't care about the order in which they have. So that's given by. Well, I had probability of success, and every time I do this, I have to multiply the probability of success. Then I have a probability of the failure every time, and that number is n minus r. So this is a binomial estimate of probability of success in n trials, and r and n are integer, but probability is any number from 0 to 1. So this is a function of n and r, which is a continuous function. Once you have this probability distribution, it's easy to compute the mean or the expectation of r. So that's just given by our probability. And also variance is easy to compute. We can now use frequentist approach to find the probability of this probability by doing, a large set of experiments. And then we can get an experimental estimate of variance, which has to be unbiased. This n minus 1 happens here. And that's how the variance works out for binomial distributions. So now, this is really easy to stick on some computer language that you feel comfortable with. Ignacio has done this, taking n samples and doing this 100,000 times, 10,000 times. And you can compute after 10,000 times the mean, which is now experimental mean, and the variance. The predicted mean is 1/2, so this is pretty good. And then you can compute, what's the likelihood that you are 3/4, 1/4 probability, and that's given by these experimental distributions. Now, in real life, there are things called extreme events. For Ignacio, the big question is that if you're going to measure one event per month, should you sit at a computer 24/7, or should you be able to take weekends off? And indeed, we have graduate students. On average, somebody is sitting at computer at all times. So typically, graduate students make the fundamental discoveries in this kind of astrophysics. Here is a frequentist observation from April 16 to October 2018. There were 16 alerts. So, I've overestimated the number of events that this humongous machine, which is, a kilometer cube of ice on the South Pole, is actually observing. And 11 of them fell on a weekend. This is just a fact. So, what's the likelihood of that? That you have 16 events and 11 R is 11. It's very small likelihood, but, it happens. It's a fact when you're doing the neutrinos. You can also compute, what's the probability that we got at least that unlucky, which means there could have been 12, 13, 14, 15, 16 events, and it doesn't help much. It's still very unlikely. So now this last thing has a name that you will often see. It's called p-value. So it's, probability that you get something or more of the something. A little reminder what Gaussian distributions that we have seen about 20 times in this course are. So the normalized Gaussian probability is centered at the mean and has a variance sigma square. Its square root is called standard deviation. But the thing that really makes sense always is the variance. In probabilities, you always look at error squared. And x is a random real value variable. So there are, two things about normal distributions. They have to be normalized. In other words, total probability should be 1. And they experimentally look like here, and I don't remember, maybe he also used 10,000 trials to compute these numbers. You do 10,000 trials, and then you in frequentist approach, you bin it along the real axis, and you measure what fraction of total number of events ended up in the bin. And, if sigma is 1, you get something of that height. Sigma is 2, you get something of that height. And there is no agreement on, what to put on the vertical axis, how to scale it. So different pictures look in different ways, but you care about relative width of the distribution. And what this sort of means is that this is half of that, because this is sigma, standard deviation. Or I can have a standard thing, but I can do measurements at different means. In that case, the Gaussian looks the same, it just shifted. Along with the normal distribution, an important concept is error function, which is defined as how much of the Gaussian distribution is centered in a finite interval, because Gaussian has the name. Now, because these things were defined again in probably by Bernoulli brothers, 18th century, 19th century, and the departments of statistics, and there are probabilists in math departments, and there are physicists, and there are chemists, and there are psychologists, there are all kinds of people. How this is normalized tends to defend our profession. So error function is defined without 1/2. And from it, we can discuss cumulative distribution function for the normal distribution. And there are various variants. So if I integrate from -infinity to x, then what I get is, and x is a positive number, I get 1/2 from -infinity to 1/2 for the Gaussian. And then the error function will be how much is left under the Gaussian when I cut it off, right? So if I cut it off, I should really, let me do it here. So this is x, and we integrated cumulative distribution. It's normal if it's computed or Gaussian, but it's used on any kind of experiment. It says, out of all my measurements, how many are smaller than this cutoff? Or you can decide to go to x and integrate to infinity. In that case, I have to subtract the error function from 1/2 to find what's in the tail at the other end. And sometimes you say, well, I'm good in measuring the absolute value of this thing.
Yeah, I know you told us you didn't want interruptions, but I figured.
No, I'm so grateful. It's unspeakable. Thank you. You're being a sweetie in a very rough world otherwise, because life of a theoretical physicist is not easy. Everybody abuses you. You'll see this when people discuss experimental data. Then you get in a really technical stuff, but it's in all experimental papers. You have to discuss quantiles. Any probability distribution, we can go to a new variable where we measure the distance in units of standard deviation. So we go from x's to t's. And then what happens is our probability distribution comes in this normal standard form with a factor 1/2, which, probabilists don't use, but physicists always use. So this 1/2 shows up here. And then you can discuss any experiments in terms of quantiles. And they can be one-sided from the left or right or two-sided. And they can be always computed in units of sigma, which is the standard deviation, not the variance. So the conventions are, if you take t in such a way that you keep 90% of the probability normalized in this way and cutting both sides, this is two-sided 1 times 6.4 sigma distribution. And if you want to be a little bit better and keep 95 of total area under the thing, you have to cut off the thing at the two sides and basically 2 sigmas. So that's what you now always see when they discover Higgs particle or they discover black hole collisions or anything that educated person should be reading about that doesn't involve Brad Pitt unless he's doing Dr. Fauci. And these are these sigmas. You can ask yourself, what quantile, so what likelihood that something has happened corresponds to given sigma, because sigma is what you can estimate from frequentist measurements. If you look at sigma that's 1, so on a normal distribution, this is a standard deviation, which is 1 or 2 across the whole normal distribution, that will capture, if it's two-sided, so you cut both tails of the Gaussian, that will capture about 70% of events. And if it's one-sided, so your machine can measure everything with a lower energy than some cutoff energies, then it'll capture about 84% of what's there. Now, the standard rule is, 2 sigmas rule. We say this is good enough. If we have 95%, and that's if I take normal distribution with 2 sigma, it'll capture 95%. And now, when they tell you probability of this not being 2 black hole collisions, it's 5 sigmas. Or, an event that I found a new particle that I haven't expected, like J psi, some particle you obtain in electron-positron collisions at high energies. If it's 5 sigmas, that's a golden standard. You believe it because it's a very, very small probability of not getting it. This is all done in terms of normal distributions to motivate, but in real life, you do the sigmas for any distribution. And you can do that because they depend on notion of accumulated distribution. So if you had very skewed distribution to the left, for example, you had Poisson distribution that I am not going to mention here, but it's in the notes. Then the normalized histogram is, you can compute sigma for any distribution. And then 1 sigma, 2 sigma, 3 sigmas correspond to cutting off your distribution at very large axis in this case, because this distribution is slowing very, very slowly. So this one was computed by taking 1 million random samples from log normal distribution, which are plain, but you should know it exists. It's easy to find. And one distribution that, it's not very natural, but intuitively makes sense to you is the uniform distribution. So uniform distribution is, you say, I have something that has value on unit interval. It's between 1 and 10 centimeters, and that's my unit interval. And now I want to say that whatever number I pick out of it, it's equally likely. That's an example of probability distribution for uniform distribution. And there are ways of producing them. Coin flips will produce this naturally, but it's also easy to do from Gaussian distribution. Now the average is obvious, it's half of this interval, and variance you can easily compute in usual definition of variance. It happens to be the length of this interval squared divided by 12.